Yeah, thanks everyone for joining our session, either in person or watch this session online. Some of you may already heard about MLflow pipelines from today's keynote, and some of you may already attended the AMA session for MLflow. So today, while we're trying to do a deep dive into the problem space and into how we derive the solution, let's first start with the problems. I want to first talk about the ML maturity levels because we know that every company wants to be a data and AI company. And we also believe that within a few years, most of the companies will be powered by both data and AI. However, if we look at the current state, many of the companies are still new to machine learning, right? So a lot of companies, they only have data processed, but they don't have any models running. And some of them may have models trained, but not in production. And then for those people who already deploy a model in production, they find it really hard to scale because every model in production requires a lot of manual efforts, right? So, and from those different stages, we often heard just common problems from our customers and about how to quickly get started with a machine learning project. This is super important for people just get started with machine learning because the best strategy for them is to quickly identify the low-hanging fruits, right? So to check where ML opportunity may exist, and then quickly go after them and see if validate those opportunities. And they have to go do really fast and to get to be powered by machine learning. And then after this stage, those companies have those models, baseline models trained, and they want to improve, focus on those impact their business the most, and try to just continue improving those models and have this iterative development. And then last, they need to ship those models into production. And this is usually the bottleneck. And the reason for that is this usually happens between two teams. One is the data science team who train the models. And the other one is either the ML engineering team or production DevOps team who owns the production environment. And they don't speak the same language, right? So the data scientist may have models trained and with a super long notebook. And they say, model is good, and let's ship it to production. And then the production engineers look at this long notebook, say, no, you cannot ship notebooks to production. You have to refactor your code and into modularized source files. And then we can just add tests to it, then well, it's ready for production. But who is doing the work? We saw two versions from among our customers. One version is data scientists spend days to learn how to use IDE, how to do the refactoring, and to meet the production requirements. And then after they meet the requirements, and they can get the models into production. But what happens after productionization is your models may not always be tracking the most recent trend, right? So the data may change, and you have to refresh your model. But when they have to refresh your model, because they don't work with those refactor, just the modularized code, they're still familiar with the notebooks. They always come back to the notebook for another iteration. And then, well, in order to make those changes into production, they have to do the refactor again, and then to ship into production. So that's version one. The complaint from those data scientists really, even a single line of change, and for the models already in production, that's super hard for them. And version two is let the production engineers own the code refactoring. They took over the notebook, tried to understand it, and refactoring it, and then from now on, this project is owned by the ML engineering team. However, while this creates a problem is the ML engineering team will start owning more and more machine learning projects, and they need to take knowledge transfer from the data scientists, and they became the bottleneck of this entire process. So either version is not good. So overall, while those are the three common problems we heard from our customers, but those are not all the common problems. For example, a lot of problem happens on the data side, right? So how you can have clean data, how you can have clean labels. But we are focusing on those three common problems with MLflow pipelines. Then, well, let's think about how we can solve those problems. And before we lock ourselves in a room and spend a week to think about solutions, and we believe, well, we are not really the first team to think about the solution. There must be some existing solutions on similar problems. I want to walk through a few kind of existing solutions that inspired the design of MLflow pipelines. The first one is when you talk about ML production, right? So let's look at the best. The company has the best machine learning infrastructure, right? So, and what they did. And that's the TensorFlow extended from Google. So it managed some Google production scale ML pipelines. That it must be very good, right? So and it introduced those pipeline concepts and with some predefined steps. Like example gen, stats gen, you can see all the steps on this pipeline. And the TensorFlow part is really in this transform and the trainer, right? So this part is use transform, but it added a few more steps and to support production use. And you don't want your schema change a lot, right? So you don't even want schema, simple change to your schema. You want to validate that. And you want to validate your model before you ship to production, not just for the model accuracy, but the infra validation as well. Yeah, this is great. And can we use it to solve our problems? Let's see what are the good things. The first one is this ML pipeline abstraction, which is really useful and for production machine learning pipelines. And then it has these predefined steps. So those data scientists, if they want to use it, they don't have to rewrite it. They can just use it as individual modules. And then they also have this embedded best practices. Right, so, and how they do schema gen, how they derive the schema, how they detect the schema changes. And those are all kind of provided by TFX. However, well, I look at the TFX tutorial, and so this is a one kind of code snippet from one of their tutorials. I feel, yeah, if I'm wearing the data scientist hats, I feel this is so hard. This is too hard to get started. A lot of code to read, a lot of code to write. And so why? Well, this is hard. This seems like it's too hard to solve the problem we want to solve. The problem we want to solve is really to enable people or companies who are new to machine learning and to get models into production. The reason this is hard is because the project was designed for Google machine learning engineers and to solve those large-scale complex problems. And they need flexibility. They need to be able to assemble their own pipelines, right? So, but for many of the problems out there, right, so machine learning problems, they are very kind of simple problems and they have very similar structure. And maybe, well, we can make some changes here and to adopt the target personas and target use cases we are thinking of. Yep. And then the second solution that inspired our design is actually Apache Maven. It has nothing to do with machine learning. And people who develop Java code and use it a lot or other build tools for Java. But I saw a question in Stack Overflow. It says, why is no one using Make for Java? And because Make can do arbitrary things. Right, so Make, you can define a build graph and use Make to build a Java projects, but no one uses it because there's already an opinionated approach offered by Apache Maven. And it has 3 components, and the first component is this called POM, and maybe many people don't even know what POM stands for because it's so popular. So it's basically an XML file that defines your project, and properties, and what plugin you want to use, and some configurations. And it's exchangeable, and you can share it, and it's already a standard. If you share it with others, and they already know what it means. Second is the build lifecycle. It's predefined, right? So you have compile, you have test, you have package, you have deploy. That address many people's developers' need for a project. So they don't need to write the make rules and for compile for test, and people may write different rules for compile for test and make it very hard to collaborate and on a project. Then they have this standard directory layout. You put your source code in source main, you put your test code in source test, right? So if you follow those guidelines, and you don't have to change anything. You just run Maven test, and everything works out. That's make Java developer life really, really simple, right? So what we can get from this project is it's very easy to get started with predefined build lifecycles and standard directory layout. It's the build tool for Java. And we can think, do we have a build tool for machine learning? Does it exist? And then it has the standardization on the POM file and for collaboration and sharing. And if you use Maven, you also know that there's an incremental build, right? So if you finish the compile and you change your kind of published destination, and it will use your compile cache and then only do this packaging stuff and then publish it. But there are also things that may not fit. The first one is this single build lifecycle, right? So test, compile, package. Can we translate to machine learning? Can we map it to machine learning? And maybe when we map to machine learning, there is no single build lifecycle can fit all the machine learning problems. Because the variety in machine learning is much, much higher than the variety in Java projects. And definitely, well, Maven was not designed to solve machine learning problems. And Maven is designed for you write code to build up a project, right? So, but machine learning requires a lot of data, and data is essential. And what's the solution for data? And can we figure out a good solution for that? And then, well, it came this popular debate between notebooks and IDEs. And a lot of people love notebooks, and a lot of people say, well, IDE is the way to go, especially for machine learning production. But we know, well, notebooks have good things. Otherwise, there won't be this debate at all. The first one is analyzing data, right? So, and the second one is interactive execution. You want to check what's the output, and then you think about what's the next command you want to type, and doing quick prototyping things. And IDEs are good for building things up, writing code, right? So, but really, do we have to choose one in our solution? And we know that production machine learning need both data and code. Yep, that helps us to think about how we design our solutions. Yep, let's go into this MLflow pipelines. The first feature from MLflow pipelines is those predefined pipeline templates. We start with a simple templates from data scientists. That's train, transform, train, evaluate, right? So this within their comfort zone. However, in order to extend it for production, and this is inspired by TFX, we want to surround it with a lot of data kind of steps and a lot of validation steps, and to make it production ready. And we do it by predefine the workflow rather than just let data scientists to construct this pipeline by themselves. And the question is it going to work, right? So this is like a one build life cycle. And is it going to work for so many ML problems out there? And we believe, well, this is like an 80-20 rule here. Many ML problems are in common, especially for the target customers or target users, and we try to help. So we can actually, instead of offer a single build lifecycle, right? So we can offer multiple pipeline templates and to address those common machine learning problem types: regression, classification, recommender systems, trend prediction, right? So we can have one build lifecycle using the Maven kind of language for each of the problem. Then it will be very easy to get started. You just shop around the pipeline templates, and which one fits your problem, take it and make a little modification, and follow our standard directory layout, and then just say change a few configurations, and in the pipeline YAML file, this is one example of the pipeline YAML file, and to get started. It will be really quick. The second one is we have this pipeline engine to help the iterative development. And if you train a model, you try to improve it, you will find yourself just jumping between those steps, right? So you modify a feature transformation, and then you try to see the evaluation results. And then you maybe change the hyperparameter, you change the evaluation result, and then you deploy and find out, oh, they didn't just pass the deployment validation, you have to go back. So the pipeline engine remember your entire pipeline and remember the dependencies between them. So whenever you make a change, it knows where your change happened, and when you try to execute a new target, it knows where to execute from. That will help you to save your time and on to some duplicate work. And next, we can also accelerate and with our opinionated dev workflows. With this opinionated pipeline templates, we're not just showing what are the steps. For each of the steps, we actually embedded our best practices. When you ingest your data, when you do the split, and we provide a deterministic split, so your record don't shift from training to validation to test. And then we also offer this distribution comparison, so you know whether your train and test and the validation follow the same distribution or not. Right? So we also provide data profiles on every step that outputs a data set. You can easily see, well, what's the summary of your feature columns and how they change over time. And we also have feature importance. We also have automatic machine learning MLflow tracking. And then on the notebook and the IDE debate, we actually designed this hybrid approach. We recommend you to use both notebooks and IDEs. You use notebook to trigger the pipeline execution. And then you use notebook output to see the rich format output, right? So we call step cards. And then you can also use notebook to load your data to do further exploration. But you put your source code, and that's critical on the critical path, and to this individual source files. And you can use IDE to develop those modularized code. So that's how we accelerate this iterative development. And last, we say for productionization handoff, you don't need to do refactoring, because if you follow this opinionated workflow, whenever you find a good model, it is ready for ship to production. You can send a PR and get it reviewed. We also offer default test suites and to help you to check schema changes and whether your pipeline runs end-to-end. Right? So those users don't need to implement those tests by themselves. And we also offer those standard command line interfaces and to integrate with CI/CD. So when you hand over a project to production engineers, you don't negotiate on what command line to trigger and what parameters to run, because it's all standardized by MLflow pipelines. So, yep, that's MLflow pipelines, and it has this three kind of solutions to address those three major problems in MLOps. And next, I want to hand it to my colleague, Jin, who led the MLflow pipeline development, and to show some feature spotlights.
All right, time for live demo. So what could possibly go wrong? I have three answers. It's Wi-Fi, Wi-Fi, and Wi-Fi. So I'm going to refresh this page to see if the Wi-Fi is good enough. We can demonstrate it on Databricks. Okay, looks it's cooperating. So today I'm going to give you a quick demo that Casey already demoed this morning about how to address a regression problem for New York City's taxi fare prediction. So this is a really age-old problems, just for demo purposes. But I want to give a little bit different taste, how this project can actually work in practice. So to set it up, I've already put this. Is it better? Okay. So this the repo into Databricks repos. So here, I call it MLP regression T1. So this is Databricks repo, and I set up as branch, I call it demo. So here, as you can see, Shenry mentioned we use a template approach to solve the problem. So first let's look at what files are in here in this template. So we want to use notebooks to give the data scientists the same feeling like we're developing in a notebook. So this is definitely something we're going to look into. So as you can see here, we have a Databricks specific notebooks. But if you are developing locally, you can also open the Jupyter notebook instead. They have the same content. But to codify this process, the pipeline, we don't put notebook on the critical path. Remember, it's just for developing and driving your local development process. So the actual pipeline configurations comes into this pipeline YAML. So we're going to quickly dive into it and see what's in there. But in addition to that, we also provide this profile structure. So give you ability to override pipeline YAML. So you're going to see why we need that in a moment. But let's just skip over and see what's in there. So this is the most important README. I'm not going to read the entire README now, but if you download the project, please go through it, and they will have all the installation instructions and how you can set it up both locally and on Databricks. Okay, so let's take a look at the pipeline YAML first. So this is the YAML file we use to define the entire project. So here we have the regression problem to try to solve. And if you think about it, we have a machine learning problem, or what do we need? We need the data. We need, this is supervised learning, so we need to know what columns we want to predict. And also, we probably want to specify what methods we want to use to actually generate the model. So here are basically what the sections define. So the first section is data. We were going to define where the data is from and in what format. And as you can see, you can also get data as a delta table if you are working on Databricks. And here is the target column. We just want to predict the taxifier. Right? And then we're going to end up into these step-specific configurations. We're going to later see what these are. For now, we can just see that we have a split, transform, train, and evaluate steps, and the final register. We can register the model. Also, you can see we provide custom metric ability. So if you have some metrics, we already compute a set of standard metrics for regression problem. But if you have custom metrics, you can define it right here. And you can also define in the Python file exactly how it's computed. All right. So now you can see in this YAML file, we have defined a couple variables here. The reason for that is that you can imagine on Databricks, you might have a bigger data set to work with. But if you want locally work with your smaller data set, that is something you can override and change here. So since we are working on Databricks, we're going to use a sparse SQL to read a sample data set from the NYC taxi data set, the delta table. So let's start with the notebook and jump right in and see what we can do here. So the first step is we instantiate the pipeline. You can see the pipeline instantiated with the profile Databricks. And then we do some cleaning. It's not strictly necessary. It's just to make sure that it's clean, the pipeline is clean, there's nothing cached, and we can just start from right here. And I'm going to run the ingest step. So while it's running, we can take a look at what the pipeline YAML defines about ingest. So the ingest, all it does is just pull the data right into your local folder so that you can work with it. So that, here we can see the data ingested, require locations, formats, and also you can provide a custom loader method. So in case you have a different format other than Parquet or sparse SQL, you can write down your own processing method right there, and all they need is to return a pandas data frame, and we can just process from afterwards. Okay, now the ingest step has finished running. As you can see, the ingest gave us a step card return. So here there are 3 tabs. And the first thing I want to see is what are the data schemas in here. So I can say, okay, from this delta table, we have 6 columns. Pickup time, drop-off date time, trip distance. Well, that's probably something I would be interested in to predict the taxifier. And also there's a pickup and drop-off zip code. We can dive a little bit into the data profile and see if pandas profiling tells us anything different, anything worth pay attention to before we actually go to next step. So here we see we have all the variables. The good thing is that there's no missing cell. That's great. And if we look at the pickup date time, drop-off time, seems all reasonable. And then we look at an important thing. This is our target column, fair amount. I noticed something different. So here, there's a minimum is minus. It's a negative $8. I wonder what happened there, that actually the cab driver gives money back to the customer. But probably it's something noisy. So we might want to do something about it before we actually train our model. OK, so this is a really simple data set. So maybe we can just start to process this data set a little bit. So here, we do something addition. We try to encode the best data science practices before we train any model. So this is where the split step is supposed to do. What it does is basically split into 3 data sets: train, validation, and test. You always use the training data to train a model. But validation, you use to do some hyperparameter tuning, but that's about it. And test, you use very, very sparingly, only to validate. After you are confident you have obtained a good model, use that to validate it actually works, and then register. Right. So since the split had finished running, we also have the data profiles for this split. They all look benign, so I'm not going to dive too deep into it. But before I go to the next step, I want to show this piece of code. So after the splits, we offer your ability to clean your data, do additional processings. Because as we have seen, the fair amount is negative. It's probably noisy, something we don't really like to train our model on. So here, we basically do this like a simple cleaning. Like the trip distance should be positive, but reasonable number, same as a fair amount. In addition, we also add a couple more features. We can do that here as well. We add the pickup date, day of the week, and pickup hour. Maybe that's useful, maybe not. But since we can derive it easily, we just do that. And in addition, trip duration, right? If you take a taxi, if you're sitting in the cab in the traffic, we will expect that the meter will keep going up. So this is probably some feature that's useful, but not present in the original data set. So we add it here. So now, with that, we can run the transform step. So here, the transformer, what I used, is I want to start with something simple, right? I don't really want to get complicated. So how about let me just use the trip distance and trip duration. This is based on my intuition. This is probably most important 2 features that will contribute to my model. Just use this, standard scale it, that's it. With that, I should have a transformer generated right here. As you can see, this is scalar and standard scalar with these 2 features input. And we can check our input schema, output schema from this transformer, only 3 columns. And now we can train our model. Right? So again, I want to use something simple. So here, I just define a linear regressor. Right? So it's an SGD regressor. Just train on this model and see how that goes. So here, as you can see, the train is running, and it started to log around to MLflow experiment. So this is where MLflow integration comes into play. As you can see, a few seconds ago, we started running, and we are already logging a bunch of metrics and parameters to this experiment. So let's come back to this later. But we can take a look at what train step card tells us. So here, the step card gives us a performance summary, not just train data set. Also, remember, we want to put this best practice in place. So here we have a training and a validation data set. So here, if you look at our primary metric, root mean square error, the train and the validation give us similar amount of errors. So that means that probably the model is reasonable, right? It's a trend that's OK. And we can also look at the profile of prediction errors. As you can see, the target. So here, something you might notice interesting. So when we look at the target profile, this is a distribution. If you zoom in a bit, you can see there's something around here. I don't know what that is. Around like $50, there's a peak. But in the prediction, there's nothing, right? So I don't know what's going on, but something worth noticing. But now we have trained one model. Can we improve it? So, right, before, maybe we can just run evaluate and quickly take a look at whether this model is good enough through some feature importance analysis. So let's give it a few seconds. Now we have the feature importance produced. So if I look at the feature, since we only have technically 2 features, but you can see there's only one feature actually is being used by this model. The other feature is not so much. That's something a little bit weird. Maybe it's not working exactly as expected. So what I can do, maybe I should train a different model. Maybe I should just use a different estimator. So here, I'm going to just switch with the tree estimator and retrain it again. So go back to train, run it again, and see what we got here. Now I notice another MLflow run has been logged to the experiment. As you can see, MLflow realized there are 2 runs being logged. One run was the previous one. The other one is just being run, still being logged, so it hasn't finished yet. So let's give it another couple of seconds. OK, now this is the tree regressor model. You can see the error goes down, right? The previous error is around 3. So can I actually see that here? You see the runs here are automatically ranked by our primary metric, root mean square error. And if I want to see it clearly, I show the difference. As you can see, the new model is doing better, right, in this case. So how about let's dive a little bit deeper. So we just replaced it with the tree regressor, right? Can we dive a little bit deeper? So here, let's take a look at the training examples with the worst performance. Can we get some insights from here? So you can see there are a couple interesting examples. The first one, our prediction is $58. The actual fire amount is 115. But if you look at the other metrics, it seems about right. There's nothing unusual jumped out. So what could be missing, I'm thinking? Maybe it's something that's not accounted for in the original data set. For example, tip amount. Maybe some customer is just really happy. They tip a fairly large amount that's just like out of ordinary. Right? That might account for this one. But it's not in the data set. So can we do something about it? There's the other kind of issues. If you look at the bottom couple rows, something jumping out around 52. So what's up with the 52? Why this $52 F-charge fire amount, but the prediction only give you like $7, even $11? What's on there? It turns out, if you don't live in New York City, probably you don't know. Well, it turns out this $50 is a fixed charge from JFK to downtown Manhattan. So if you say you take your cab from JFK to downtown Manhattan, but you forgot your luggage, like you realize like on the way, they can very easily to generate this kind of data set. Like give you, your predictions are you only drive a small amount, but you still charge a large amount of the fixed fees. So this is something we not captured in the data set, original data set. So I think engineering mentioned like you always look at our data first. So I think this is probably a good example. We can now start thinking about it. Go back to our data engineers, say, hey, can we get more columns about the tip amount? Can I get, maybe I should try a more accurate columns, for example, started from airport. If I have that, maybe I can improve my model upon. So I think my time is up. Let me just run one more time on evaluate and see what we got here. So let's give it a few seconds. All right. So as you can see, our model performs even better on test data set. Surprise, surprise. Maybe it's not something we actually want, or maybe it is. But at least with this tree model, we have a better understanding of what's going on. And also, we have, if you look at the feature importance, both trip distance and trip duration are being fully utilized. So I think I'll just end here. Time for quick questions?
Yeah, we can probably take a couple. Get one up here.
Hey, thank you so much. What gets written into MLflow? Does it capture the images, or does it capture these kind of step-through pieces?
OK, before I answer your question, one more thing. If you want to try MLflow pipelines, scan this QR code. You can try that right now. And there's a README and everything. You can just download from there. All right. Okay, do you mind to repeat your question?
Yeah. What gets written into MLflow at the moment? Does it capture the images currently, or are any of the parts that are auto being generated, are they ending up as artifacts in MLflow?
Great question. Yeah, I think we logged the major output from each step, like the step card you see. So you can always go back to the runs and look at it. So let me just quickly show you what's in there. So for this particular run, we log the pipeline snapshot, the exactly code you use to generate this pipeline run. And we log for your models, of course, in train step. And you see your model, your estimators, your transformers, and for all the step card. So
Brilliant.
You can always go back to look at what you did in that particular run and figure out what's going on. And finally, I forgot to demo is the leaderboard, but you can give it a try and see how it basically compares your current run with your previous best 2 runs. Yes.
Thank you.
All right.
We can do maybe one more question. Oh, yeah.
So thank you for the demo. That was really great. I have a question on the kind of APIs you have. So you showed the demo in Python, but we have code in C++. So I know MLflow has a REST API, but is pipelines going to be supported with that? Just wondering, like, what kind of APIs we can use if we are not doing Python-based coding.
So you're asking for APIs for MLflow pipeline itself?
Yes.
So right now, we have released MLflow pipelines into MLflow 1.27. So it's all open there already. However, I would caution it's experimental. So those API might change. Actually, this is the time I want to ask for everyone here to contribute their ideas and give it a try and tell us what it works, what it doesn't. And since it's experimental, we're going to change it, and your feedback will be very valuable to actually be taken into account. Thank you.
That's good. Thank you.
We can squeeze one more. This will be the last question. If you have any more, please catch them in the hallway.
Yeah, hi. Thanks for the presentation. Can we add to the pipeline hyperparameter optimization?
Yes, great question. We can actually, so this is something we already been thinking about to integrate AutoML into the train step. Hyperparameter tuning is definitely in there. So actually, right now, you can also use scikit-learn built-in hyperparameter tuning in the grid search without problem. Because all we ask for is just the estimator, and the grid search is an estimator.
Thanks, everyone, for coming. Give them a round of applause.